Hello everyone, my name is Yiming and I'm a third-year PhD student at University of Rochester. I'm working with Professor Yuhao Zhu. It's a great honor to be here to present our work, Ptolemy, Architecture Support for Robust Deep Learning. This work is a collaboration between our group and researchers in Shanghai Jiao Tong University. We have a point. Deep learning is vulnerable. It is not robust. It can be easily fooled by some manually carefully designed examples. We show two stop signs images here. One is what we get from the dataset, and the other one is what we designed to fool the system. They look exactly the same, but can result in different classification results. These type of examples are called adversarial examples, where people created by adding carefully manually designed perturbations to the original image. And these adversarial examples can easily fool the system. The stop sign here on the right-hand side will be classified as something else, which makes the system vulnerable. However, deep learning is now used in a lot of mission-critical applications, such as advanced driver assistance systems and security cameras. Thus, to ensure the robustness of deep learning systems against the attack of adversarial examples is important. We think there are 2 points of counter-adversarial examples. The first one is detection accuracy. The countermeasure should be able to accurately detect the adversarial examples. Meanwhile, the detection approach should not bring significant overhead to influence the inference procedure. Thus, we propose Ptolemy, a software-hardware co-design to counter adversarial examples. Our system is able to accurately detect a wide range of adversarial attacks, as well as maintaining overhead to a very low level. The key concept we use to detect adversarial examples is what we call path. We got this idea from the traditional software development. When we look at traditional software, both program analysis and program optimization always use the idea of how path, which is multiple of frequently exercised basic blocks. This type of information extracted from runtime can help making the programs run faster or contribute to debugging the program. We think that similar to traditional software, neural networks can be treated as another type of software. Previously, when countering adversarial examples, there were people thinking of using runtime information. However, during the network inference, some neurons and their connections are contributing more when generating the outputs, which will formulate a hot path. And this hot path can help us on detecting adversarial examples. We here show the basic way of identifying important neuron. We have a simple example of fully connected layer where the input feature is a 1x5 vector and times a 5x3 matrix. The path definition starts from the loss layer. We find the largest value in the output layer, which is 0.46 here. This value will be the most important neuron on the last layer, as well as our starting point. 0.46 is an accumulation of 5 partial sums. We further sort all the partial sums and add them back. After the sorting and accumulation, we find out 2 largest values have already contributed to more than half of the total sum. Thus, we identify the most important 2 values on the input feature map, which is 1.0 and 0.1. Similar to FC layer, we have an example showing how it works for convolutional layers. Please refer to the paper for more details. So basically, we can find important neurons on the previous layer. And we iteratively do the same process on these 2 important neurons to find the important neurons on the layers before. All the important neurons and their connections formulate the paths we will be using. So now we can extract important paths in one single image. We further will formulate the common important paths of the same class. Taking cat's class as an example, during training, we will formulate important neuron paths for all the individual cat samples. Each cat sample will have their own important neuron path. We union all these paths belong to cats to formulate class path for cats. So at the end of training phase, we will have one common important neuron path for every class. We here compare the difference between different classes' paths to show that they're distinguishable. We use the heat map of ImageNet dataset with AlexNet as the classification network to present the difference of class path. Both x-axis and y-axis represent different classes. We randomly pick 10 out of 1,000. In this heat map, the deep the color is, meaning the higher similarity between two class paths. The similarity ranges from 0 to 1. 1 means two class paths are exactly the same, while 0 means they have nothing in common. As we can see in the results, except for the diagonal, all the similarity have a very low value. The diagonal is all 1 because it represents similarity between one class and itself. The average class path similarity is only 0.36. Representing one class path is significantly different from all other class paths, and they're all distinguishable. The basic idea we'll be using for detection is that, although adversarial examples may fool the system, its inherent paths will not be changed. So as long as we compare the adversarial example's paths with corresponding class paths, we will be able to tell if they are a match or a mismatch, which could help us to detect adversarial examples. For example, we have an input coming, which we don't know if it's an adversarial example or not. Our system gave a classification of the input, which is a cat. Meanwhile, we extract the input's important neuron path. We use the individual paths to compare with the cat's class paths we got from training, and we compare two paths to see if they're matched or not. If it's a match, we think this is a normal example. Otherwise, we treat it as an adversarial example. So here's how Ptolemy pipeline looks like. The inference starts from the first layer and goes all the way to the last layer. After that, the extraction starts from the last layer and goes backward to the first layer. The pipeline looks like this. As we can see, this execution pipeline brings a significant amount of overhead, so we design some variation knobs on the algorithm framework. The first design knob we propose is enable the extraction to start from the first layer. Thus, we can pipeline extraction with inference. Again, inference starts from the first layer. But this time, extraction also starts from the first layer. So the extraction and inference can happen at the same time, like this. By pipelining inference and extraction, we can largely reduce the overhead. The second knob is the way of identifying important neurons. Originally, Ptolemy needs to sort all the partial sums and add them back to decide whether it's important or not. This is obviously time and energy consuming. We propose to use thresholding to replace sorting, where we compare each partial sum with a threshold. The third knob we provide is partial extraction. Ptolemy needs all layers information to form a path, which we find is redundant. We try to reduce the number of layers of Ptolemy, and which we call partial extraction. We propose a framework that covers all the variations. Users are able to decide whether they want the algorithm to start from the first layer or last, use sorting or absolute, or thresholding, or they can mix some of the parameters. For example, a point, this design point here representing user want to use backward, use sorting, and use full extraction. With all the parameters of algorithms and different knobs, we present a high-level programming interface for users to translate their specifications of Ptolemy, where a user can define things like extraction direction, sorting or thresholding, etc. Our customized compiler will transfer the high-level program into low-level instructions. During compilation, we apply two different optimizations to enable different level of pipelining. Our compiler mainly tries to maximize the performance. The first one is layer-level pipelining. Originally, the codes look like this pseudocode, where inference and extraction is executed serially. Our compiler will leverage the traditional software pipelining techniques to reorder the instructions. So the inference of layer G+1 and the extraction of layer G could happen at the same time. The second is neuron-level pipelining. Similar to layer-level pipelining, when we use sorting, for each neuron, sorting all the partial sums and add them back was serialized because of the data dependencies. The compiler overlaps the extraction across different neurons, pipelining, sorting, and accumulation to improve the hardware utilization and performance. Here's the architecture overview of Ptolemy. Our architecture builds on top of a conventional DNA accelerator. It consists of an augmented DNA accelerator, a path constructor, and a controller that dispatches instructions, runs the machine, and handles final detect decision. With more hardware details can be found in the paper, I want to explain how we enhance the Mach unit of the baseline DNA accelerator. Originally, in the thresholding method, we need to read out each partial sum and compare them to a threshold, and store the important mask back to the SRAM, which makes the memory bandwidth becoming a bottleneck. Our enhanced Mach unit design is to directly compare the partial sum with the threshold in the PE and only save the importance mask to the SRAM. Through this minimum change to the Mach, we're able to achieve inference and extraction at the same time. Next, we will show the results of Ptolemy. We did our evaluation on multiple networks, including AlexNet and ResNet. We also open source our code and provide scripts to test VGG and MobileNet. Please refer to the GitHub repo for more information. We use CIFAR10, CIFAR100, and ImageNet as our datasets. And to test the robustness of our system, we tried a wide range of attacks. Besides many well-known attacks such as deep fool, we also construct a type of adaptive attacks, which we assume the attackers have gained both the model and our defense mechanism, so that they can create more specific attacks. We also welcome researchers to try to break the defense of our system. The baseline we use is EP and CDRP, which are two state-of-the-art detecting mechanisms. We evaluated multiple instances of Ptolemy. Type 1 is using backward sorting and full extraction. Type 2 is using backward thresholding and full extraction. And type 3 is using forward thresholding and full extraction. We evaluate Ptolemy using a 20 by 20 DNA accelerator with a 1.5 MacBet on-chip SRAM. We feed the parameter into a cycle accuracy simulator. We first show the detection accuracy of Ptolemy. On y-axis, we show the detection accuracy. On x-axis, we show the different instances and our baselines. The type 1 has the highest accuracy. This is the original Ptolemy. The green bar shows that the detection accuracy is 0.93. As we show in the chart, almost all Ptolemy instances show better accuracy compared to the state-of-the-art models. As we're trying to use forward direction to replace backward and use absolute threshold to replace sorting, we find that the accuracy will have a drop as they are more of an approximation. One of the main goals of our work is to reduce the detection overhead, which we will show in this figure. Again, x-axis represents different instances and y-axis represents the overhead. We normalize the overhead to inference latency and energy. So the lowest overhead will be 1. Again, type 1 has the highest latency and energy overhead. It consumes almost 8 times energy and 12 times latency compared to inference. Because it starts from the last layer, it has to wait until all the inference finish and use sorting, which consumes significant amount of time and energy. Other than that, all Ptolemy instances show significantly less latency and energy overhead compared to the baseline. And it's clearly shown in the graph, when we use absolute threshold to replace sorting, both latency and energy overhead is largely reduced. And when we change the direction to forward, the latency overhead is even more reduced. In AlexNet, the minimum overhead is only 2%. As conclusion, we introduced Ptolemy, an algorithm architecture code design system that detects adversarial attacks at inference time with low overhead and high accuracy. We exploit the synergies between DNA inference and imperative program execution. Critically, we observe that adversarial examples tend to activate distinctive passes from those of benign inputs. Leveraging this insight, we propose an adversarial detection framework, which uses candidate passes generated from offline profiling to detect adversarial examples at runtime. We provide a high-level programming interface that allows programmers to explore the critical trade-off between detection accuracy and efficiency. The Ptolemy compiler, along with the co-designed hardware, enable efficient execution by exploiting the unique algorithmic characteristics. We thank the collaborators Yuxian, Jingwen, Minyi, and Yuhao. And it's a pity they cannot be here because of the COVID-19 situations. And thank you for listening. I'm happy to take questions.